These springs are made from the same steel and pulled with exactly the same force, yet one extends twice as far. If the material is the same, why is their response different? Make the prediction now. Density is mass per unit volume. Rho equals mass divided by volume, measured in kilograms per cubic metre. Halving a uniform sample halves both mass and volume, so density remains unchanged. A metal cube, side 2.0 centimetres, has mass 63 grams. In SI units, its volume is 8.0 times 10 to the minus 6 cubic metres. Divide 0.063 kilograms by this. The density is 7.9 times 10 to the 3 kilograms per cubic metre, which is consistent with iron or steel. The common trap is the cubed unit. 1 centimetre is 10 to the minus 2 metres, so 1 cubic centimetre is 10 to the minus 6 cubic metres. Therefore, 1 gram per cubic centimetre is 1,000 kilograms per cubic metre. Convert the length before cubing and then check the scale. For a uniform material under fixed conditions, density is intrinsic. A hollow or composite object has an average density. The springs have the same material density. Their different extensions are described by the spring constant. The first spring is 0.200 meters long. Once a 3.2 Newton load has settled, the spring is 0.280 meters long. Delta L is the difference, 0.080 meters. Extension is the change, not the final length. In the proportional region, Hooke's law says that F equals K delta L. The spring constant K is in newtons per meter. Larger K means a stiffer spring. Here K is 3.2 divided by 0.080 or 40 newtons per meter. Plot force vertically against extension horizontally. The straight line through the origin has gradient K. Reverse the axis and it does not have gradient K. The other spring has the same material density, but a thicker wire and different K. The spring constant describes the whole object, it's not just a material property. The area under the loading curve is the work done. In the Hookean region, it is a triangle, 1/2 F delta L or 1/2 K delta L squared. Here it is 0.13 joules. If the spring is elastic and losses are negligible, that energy can become kinetic or gravitational potential energy when the spring is released. Increase the load and the graph eventually stops being straight. This is the limit of proportionality, where Hooke's law ends. This response can still be reversible. Below the elastic limit, removing the load restores the original length, so that limit is established by unloading. Beyond it, deformation is plastic, and then a permanent extension remains even after you've unloaded it. On a simplified metal spring graph, plastic unloading is roughly parallel to the original elastic line, but meets the extension axis to the right of 0, so that intercept is where the permanent extension is. The loading area is the total work done, the unloading area is the energy returned. The difference is not returned mechanically, but it is dissipated mainly through heating and permanent structural change. Once the curve bends, 1/2 F delta L no longer gives total work. Use the area under the actual curve. Keep the labels precise. Rho describes a uniform material. F equals K delta L describes a particular spring only in its proportional region. On a force extension graph, gradient gives K, area gives work, proportionality ends at the first limit, and then reversibility at the second limit. The two springs have the same material density, but different spring constants. Next lesson we'll be looking at stress, strain, and the Young's modulus. We'll separate out material stiffness from specimen geometry.